So this is going to be a lot gentler and kind of more methodical introduction to some model fitting issues. And I want to preface this with a little spiel about model fitting. So sometimes you read in the paper, or you may have done this yourself, where you see something like, we did a model-free analysis of something, right? And that could mean various things. It could mean that we did clustering, or we did PCA, or we even just did things like ANOVAs and t-tests and regression and stuff like that. No, that is not model-free. In fact, nothing you do is ever model-free. Everything is based on a model, whether you like it or not. So t-tests, regression, ANOVA, that's all based on various kinds of linear Gaussian assumptions about your data. And so the question that's facing you is not, am I using a model or not, but which model do I want to use? And so what I want, and this is kind of a piece with my last lecture, which is that you must think generatively. That's the only way to draw sound inferences about your data. You have to think about, are these reasonable assumptions about my data? And if not, what are better assumptions about my data? And what I'm going to present to you here are kind of generic tools and ways of thinking about this question, ways to build models, what the mathematical principles underlying them are, ways to compare them, ways to fit their parameters. And this applies to essentially everything that you do. It just happens to be the case that when you run an ANOVA, all of that model fitting and comparison and so on is going on under the hood. Okay. So here's the basic concepts. And I'm not sure how much of this I'll get through. And I think the best way to do this is for you guys to just interrupt me at any time and ask questions. And I don't really care how much of this I get through. Okay, so I'll talk about some basic probability theory concepts, estimation and model comparison, and show how these are applied to linear regression. Okay, probability theory seems kind of intimidating, but really you can go a really far way by just knowing two rules. In fact, you can derive all sorts of things by knowing these two rules. For example, you can derive Bayes' rule from these two rules. So the first rule is the product rule. So if I have two random variables A and B, the joint distribution, the joint probability of those two random variables is equal to the product of the conditional and the marginal. So you should try to remember these terms because they're kind of ubiquitously useful. And because this is symmetric, you can also just reverse the order of these things. So the second rule is the sum rule, or sometimes known as oh yes, go ahead.
Can you define those terms, joint, conditional, marginal?
Okay, yes. And actually, yeah, let me just show you this example, and then I'll come back to this. So imagine that we wanted to ask, what's the probability? So we have two random variables. One is I'm wet or I'm not wet, and the other is it's raining or it's not raining. So I could get wet for various reasons that may be due to rain or not due to rain, and it could be raining or not. So I have this two-dimensional binary space that can be represented in this 2x2 contingency table. So this is the joint distribution. These numbers have to sum up to 1. And what this number is saying is, what's the probability? This number is saying that this is the probability of being wet and it's raining, and this is the probability of not being wet when it's raining, and so on. So there's two things that I might care about here. One is the joint probability, right, which we can basically read off of this table. The second is the marginal probability. So if I want to know what's the probability of being wet, what the sum rule says is that I'm going to sum over all the different ways that I could be wet, right? So if I want to know the marginal probability of wet, I sum the probability of wet while it's raining, the probability of wet while it's not raining. And that gives me the marginal probability of being wet. Now notice that this factorization of the joint distribution into the product of a conditional distribution and a marginal distribution can lead us to another very useful observation. Oh, sorry, I have it. I'm going to come to that later, but basically we can use that factorization to derive Bayes' rule, and I'll show you that a little bit later. Okay. Now again, sticking to this theme of thinking generatively, we want to think about these probability models as defining generative hypotheses about how our data are different. So we can think about the joint distribution as arising from a particular generative process. In other words, when I take this joint probability and I factorize it into these different conditionals and marginals, a really intuitive way to think about this is as a kind of causal model. So I can say that let's just go back to the rain example. So I want to know why did I get wet? So one hypothesis is that it was raining, but I need to know what's the probability of it raining. Or actually, that's a better example is will I get wet? So a possibility is that I will get wet because it rained, and I need to then know what the probability of rain is, right? So so I need to take the probability of rain and then the probability of getting wet because it was raining. So the factorization yields a kind of a representation of the underlying causal process. And one useful way to represent this is in terms of a graphical model, and you've probably seen this before. Each of these nodes corresponds to a variable, and the shaded nodes correspond to observed variables, and the unshaded nodes correspond to unobserved or latent variables, and the arrows represent probabilistic dependencies. So this is saying, the way to read this is saying that I have some parameters that generate my data. The parameters are not observed and the data are observed. And you can, from this graphical model, you can read off a particular decomposition of the joint probability to say that, again, that the probability, the joint probability of the data and the parameters factorizes into the probability of the data given the parameters and the probability of the parameters. So this is called the likelihood in Bayesian terminology, and this is called the prior. This term is saying how likely were the data that I observed given a particular choice of parameters? How well does the data match my expectations? And then the prior tells you how plausible this particular setting of the prior is, of the parameter. All right, and so don't worry about this derivation. But I just put this up here because to show you that it's quite straightforward by applying these product and sum rules to derive Bayes' rule. So you can show that the posterior probability of the parameters given the data is proportional to the likelihood times the prior, and then divided by this normalizing constant, which is called the marginal likelihood. And the marginal likelihood will come up later when we talk about model comparison. All right, so I have my data, I have my hypothesis space of parameters. Now I want to estimate those parameters, and there's different principles for estimation. And again, I want to emphasize that thinking generatively about your data, writing down a generative model, in other words, writing down a joint distribution on parameters and data, is quite separate from how you fit that generative model or evaluate it. So these different parameter estimation techniques are sort of orthogonal dimension to the model fitting process relative to the generative model. So these model fitting, these estimation algorithms, objective functions can be applied to any particular generative model. And moreover, even for a single objective function, there are many different ways to optimize it. So that gets into algorithmic questions. And I'm not going to talk too much about that, but I want to try to convey to you that you can separate these different components in your heads, because I think they're often kind of confused in various treatments. So the standard way to fit parameters is maximum likelihood. So the idea is that I'm going to take my likelihood function and find the value of the parameters that maximizes that likelihood. I should be using a pointer. So that's called the MLE, or the maximum likelihood estimate. Notice that I've ignored the prior. If I add in the prior here, then I get maximum a posteriori. So now I'm combining information about the fit of the data, the fit of the model to the data, and this prior on my parameters, which acts as a kind of regularizer. So it tells the objective function that that it should favor certain parts of the parameter space over others a priori. Both of these are what's known as point estimators. So it gives you back a single value of the parameters that optimizes the subjective function. The alternative is to get a distributional estimator, where what I get back is a complete posterior distribution over the parameters given the data. And this is known as the Bayesian estimator, and that's essentially just applying Bayes' rule. That looks simple, but for interesting models, it often is not simple, and we need to do some kind of approximation. We saw that before that in my lecture, that I had to use some fancy techniques to get an approximate posterior. There's some practical issues here that all of you will run into if you ever do write down model fitting code. So practice, we don't want to optimize products of probabilities. We want to optimize logs because those are more numerically well behaved. And so if you have a bunch of independent data points, the joint probability of those data points factorizes into their product. But if you multiply a bunch of probabilities that are bounded between 0 and 1 together, then you get this really small number, and if you do that enough times, you get a number that's so small that your computer can't even represent it. But if I take the log transform, then I'm summing a bunch of logs, and that is going to avoid numerical problems. And just to be clear, that summing log probabilities is fine from the point estimation standpoint, because the maximum likelihood and map estimators are invariant to a monotonic transformation of the objective function. Okay. Why use priors? Why should we give up some fit to our data in favor of some parameter values over others? The key problem here is that you can overfit. Basically, your data are noisy, and you can draw incorrect inferences if you don't impose some constraints. They could be hard or soft on the kinds of parameters that you can get out of the model fitting. And the basic consequence of overfitting is that if you fit to the noise rather than the underlying signal, then when you try to generalize to new data, you're going to fail. You're going to get higher generalization error compared to if you have some regularization on your parameters that, for example, that's induced by a prior. Now, map estimation does this kind of regularization in a point estimation framework, so it will constrain your point estimates to be within some preferable region of the parameter space. Bayesian estimation does that too, but now you're estimating an entire distribution. So why would you want a distribution relative to a point estimate, assuming both of them are doing some kind of regularization? The reason is that the point estimate basically gives up all representation of uncertainty. So you can't quantify your uncertainty, and you could have really strong evidence for a point estimate or really weak evidence, and you wouldn't really know the difference. I'm going to show you later a kind of clever technique to basically get uncertainty out of point estimates, and I'll explain what that means in a second. So on the topic of uncertainty, the standard way in a frequentist context to quantify your uncertainty or variability, I hesitate to even use the word uncertainty here, is the confidence intervals. That's really saying that if I repeatedly collected a bunch of data sets and estimated the parameters of my model, then the true parameter would fall within that confidence interval some percentage of the time. With Bayesian analysis, it's quite different. So we no longer have this kind of frequentist interpretation of a confidence interval. Instead, we have credible intervals, which are fundamentally different. So they're quantifying your subjective uncertainty about the underlying parameter. What it's saying is that the posterior probability that the parameter's true value is within that credible interval is some probability. So I can define, let's say, a 95% credible interval says that 95% of the probability mass is within that interval. It turns out that you can actually get confidence intervals from the Hessian, which is the matrix of second derivatives. And this is something that numerical optimizers like in MATLAB typically construct for you as part of their optimization procedure. So you can basically pull that out of the optimization. And I'm not going to go into the mathematical details, but basically you can take that Hessian and compute within subject confidence intervals. And in particular, the inverse of that Hessian is an estimator of the covariance matrix. So the diagonal elements represent the variances for the individual parameters, and you can get 95% confidence intervals basically by multiplying that by a factor. It also tells you something about the covariance between the parameters, and that's actually really useful because a lot of the models that we care about are actually not identifiable. What that means is that the model has a bunch of different parameters, and those different parameters are partially explaining the same variance. And so what that means is that when I fit some data, I can't unambiguously figure out which part of the variance one parameter is explaining over the other. That matters a lot if I want to do, for example, some individual difference analysis. So let's say I'm fitting some reinforcement learning model with a learning rate, and I want to know whether the learning rate covariates with some other thing across individuals. Well, the problem is that the learning rate is partially confounded with the inverse temperature, which I'll show you here, actually. So if you plot the likelihood surface, anyone can do this. You can take a simple reinforcement learning model and plot the likelihood surface as a function of the learning rate and the inverse temperature. Sorry for those of you for whom this terminology is unfamiliar, but I'm just going to explain the basic idea. Its application to a particular model is situation specific. But the idea here is that there's actually this region in which this equiprobability region where different settings of the learning rate and inverse temperature give the same likelihood. That means that there's no way for a maximum likelihood estimator to tell the difference between any of those solutions. They're all equally good. And that's problematic for interpreting things like individual differences. So one way to constrain, one way to deal with this identifiability issues is to try to constrain the parameters, to basically try to restrict that parameter space in such a way that the region of this equiprobable contour is smaller. So for example, the inverse temperature should not be allowed to be arbitrarily large. If you assume that there's always some irreducible stochasticity in a subject's responses, then the inverse temperature can't be arbitrarily large. And what I'm really appealing to you here is, again, to think about the generative assumptions. Is it possible that a person could have an inverse temperature of 1 billion? If you don't think that's possible, then you should place those impose those constraints on your model, right? That's a way to use both common sense and in some cases even quantitative techniques to determine the appropriate priors for your data. And you don't have to put these kinds of hard constraints like a cutoff on the inverse temperature. You can do it in a soft way by using distributions, using prior distributions. So it says that it would prefer to have the inverse temperature in some range, but it can be convinced to deviate from that range if the data is strong enough. Any questions so far? Another really important thing that we need to do a lot is model comparison. So I'm going to just give you a simple case where we have two models, but the logic basically applies the same to more models. How do I choose between them? The Bayesian approach is to compute the posterior probability over models, right? So now I have some data, I want to compute the posterior probability over models. How do I do that? So let's go back to Bayes' rule for parameters. So remember there's this normalization constant, which I kind of glossed over, the marginal likelihood. Now if you look, the marginal likelihood is the likelihood of the data given the model after we've averaged this over all the parameters. So we've marginalized out the parameters. And that marginal likelihood is in fact the likelihood function for this posterior over models. So what that means is that if my prior over models is uniform, which it usually is, then my posterior is simply proportional to that marginal likelihood. In other words, the marginal likelihood, that normalization constant which we were kind of ignoring before, is actually super useful for doing Bayesian model comparison. And one kind of neat thing that comes out of this is that you don't need to express a preference for simplicity to get a preference for simpler models. So this is known as Bayesian's Occams Razor, and it comes out of the way that the marginal likelihood works. And the basic idea is that if you have a complex model, you can fit lots of different data sets. But any given data set gets less probability because the probabilities have to sum to 1. It's like the complex model is kind of betting on all these different data sets. And when it gets some particular data set, it can fit that, but it sort of put a lower bet on that data set. Compared to a simple model, if it can explain that same data better with fewer parameters, then it kind of wins big because it bet a lot of money on that, a lot of probability on that data set. So this is a famous diagram that's due to David Mackay, where we basically ordered all the possible data sets of some size, and a simple model concentrates its probability mass in this region of the data set space. So these are the data sets that you can predict really well. And then here's a really complex model in blue that can predict lots of data sets, but any one data set it doesn't give a high probability to. And then there's a just right data. So if you look here, so the simple model basically completely fails to predict the data. The complex model predicts the data, but it's not putting so much probability mass on it. And then there's this just right model of intermediate complexity that puts just the right amount of probability mass on the data set. Just a note on terminology. Sometimes people report the results of model comparison in terms of Bayes factors. These are just ratios or logs of ratios of marginal likelihoods, or really of the posterior probabilities. But if you have uniform priors, then again, these are just ratios of marginal likelihoods. And this is just another way of reporting the same results. Right. So how do you actually compute it? Marginalizing over all the parameters is typically intractable. I put a sum here, but typically the parameters are continuous. So what you really have is some possibly high-dimensional integral of the likelihood times the prior to obtain the marginal likelihood, and that's intractable. How are we going to approximate it? The Bayesian information criterion, which I'm sure many of you have heard of, can be understood as a kind of asymptotic approximation of the log marginal likelihood. So it has this first term is just the log likelihood of the data using the maximum likelihood estimate, but this could also be the map estimate. And then the second term is the complexity penalty. So your complexity penalty scales with the number of parameters k, and then the number of data points. But there are some problems with this. This is super convenient to compute, and lots of people compute it. There is a problem, which is that it's only valid when n is large relative to k. So when the number of data points is really large relative to the number of parameters you're trying to estimate. And it assumes that the posterior is approximately Gaussian. And that might seem kind of crazy, but actually it's well-founded because it turns out that for many models, if you have enough data, the posterior increasingly approaches a Gaussian distribution over the parameters. That's known as the Bayesian central limit theorem. And if you get an infinite amount of data, then that Gaussian posterior basically collapses onto a single point at the maximum likelihood estimate. So what it's essentially doing is taking kind of an approximation of the volume of the posterior around that maximum likelihood estimate. And in fact, as I'll show in a moment, that can be derived from a different kind of approximation. I'll just mention one other thing, which is that it's actually not straightforward at all to compute BICs when you have dependencies. So for example, you have time series. Now the data points aren't dependent. Or you're trying to compute it for hierarchical models where like your subjects aren't dependent. So it runs into some conceptual problems there as well. The BIC can actually be understood as an approximation of an approximation. So there's a technique that's known as the Laplace approximation, which is not very widely used in neuroscience, but it's actually quite useful to know about and even to use. And the idea here is that remember I told you that if you have enough data, then your posterior is going to be approximately Gaussian around around the peak of your posterior. That's the map estimate. So what I can do is I can basically take what's called a Taylor series expansion around the peak of that distribution. What I'm essentially doing is assuming that the posterior is roughly linear, or the log posterior is roughly linear around the point estimate. And if I do that, then I can get a closed form expression for the marginal likelihood. And that's known as the Laplace approximation. It uses the H matrix, the Hessian matrix that we saw before, the matrix of second derivatives. So it turns out that in addition to getting confidence intervals, the Hessian matrix is useful for approximating the marginal likelihood. And the BIC is basically an approximation of this when when in the asymptotic limit of infinite data. So I should have mentioned this earlier. I have a model fitting toolbox. There's a GitHub repo for it. It's called MFit, and I've implemented all of these things that I'm telling you about. So if you want to try any of them out, you can use it. It's basically just an interface to various procedures in MATLAB, but I tried to set it up in such a way that it's user friendly and kind of a lot of the more mundane stuff gets done under the hood. So what I've been talking about so far has implicitly assumed that when we do model comparison, we're trying to find a single model that explains all of our subjects. But that might not be reasonable because some subjects might be better explained by one model and some subjects might be better explained by another model. So what we'd really like to do is allow for different subjects to be explained by different models and try to estimate the frequency of a particular model in the population. And that's what's known as random effects model comparison that was pioneered by Klaus Stefan. So the idea is that we're going to write down a generative model according to which for each subject I'm going to sample one of the models from some unknown distribution, and then I'm going to estimate that distribution over models given my estimates of my observed marginal likelihood. So the workflow here is that I get some data, I fit the model, I try to approximate the marginal likelihood for each subject separately, and then I enter that into the random effects model comparison, and it will try to estimate the frequency of each model in the population. So the graphical model looks something like this. Don't worry about all this notation here, but this is just reiterating what I just said. And what you get there's various ways to quantify that. The most common way is to use what are called exceedance probabilities. So this is the probability that a particular model is more frequent in the population than all the other models. And actually, it's become more standard to compute what's called the protective exceedance probability, which accounts for the possibility that the differences arise from chance. So usually, I think by definition, protected exceedance probabilities are always monotonically related to the exceedance probabilities. They're just more conservative. You'll get less extreme protected exceedance probabilities compared to the exceedance probabilities. And this was initially implemented in SPM because this is done by the SPM developers, but I've ported it over to my toolbox so that it can run independently. Now I've been talking a lot about Bayesian model comparison, but that's not the only way to go. And arguably, an even better way to go is to do cross-validation, because now you're really estimating the held-out accuracy of your model. Ideally, you should be able to do both of these, and they will agree with each other, but sometimes they don't agree with each other, and you have to figure out why. Okay, I assume probably everyone is familiar with cross-validation here. And I'm not going to go into this, I'll just briefly mention there's another criterion that people sometimes use, which is called the Akaiiki information criterion, or AIC, which looks a lot like BIC, but it's strictly less conservative with respect to model complexity. So the penalty on model complexity is lower because it doesn't scale with the number of data points. And there's basically its derivation is quite different from the Bayesian model comparison. It's based on information theoretic principles. I tend to disfavor AIC for the following reason, which is that a lot of the time when we're doing model comparison, our hypothesis is a complex model that we want to compare to some simpler variations. So I think it's reasonable to ask that our model comparison metrics be biased against complex models so that we make sure that we're not getting too many false positives in terms of fitting lots of complex models, because this could be very permissive. You could accept all sorts of complex models. But in general, it's actually quite useful to generate data from the models and then use BIC or AIC or whatever else, Laplace approximation, to see how well model recovery does. So one thing you'll find for a lot of models is that actually BIC may fail to recover a complex model even when you've generated data from it. And that should be a warning signal to you that you probably shouldn't rely on it too much if you're trying to analyze real data. All right, so let me illustrate these ideas to you in a linear regression model. I spent the last lecture bad-mouthing mass univariate models, but now I'm going to tell you about mass univariate models. So let's imagine that we're modeling ephemeridis, so we have some bold signal that corresponds to a vector y of the data, the patterns across boxes, and we have a bunch of covariates, and we have the regression coefficients. So the likelihood function is just this linear Gaussian model where we have some measurement noise sigma squared, and then the linear covariate-dependent superposition of these coefficients. And the one thing that we're going to do a little bit differently is instead of just estimating the maximum likelihood estimates, which is the standard thing to do in fMRI analysis, we're going to place a prior on these coefficients, a Gaussian prior that favors them to be smaller, closer to 0. And when you make these choices, it turns out you can do this there's a closed form solution to getting these regressions, getting these coefficients out. It's called ridge regression. But let me just, instead of showing you that map, which is not so helpful, let me just express this in terms of an objective function. So if you remove a bunch of constants, we take the log transform and remove a bunch of constants, MLE is basically minimizing the sum squared errors between your predictions and the data. And the map estimate is minimizing a regularized sum squared error. So it still has the sum squared error term, but now it has the second term, which is penalizing large coefficients. I think that's helpful it's helpful sometimes to write down these objective functions to see what it kind of illuminates what the properties are of the models that you're trying to estimate. So here's some intuitions. Notice that there's this weighting factor here, sigma squared relative to tau squared. So remember, sigma squared is your measurement noise, and tau squared is your uncertainty about your prior. So when your data are noisier, large sigma squared, then you're going to upweight this prior. In other words, when you trust your data less, you're going to lean more on your prior. And likewise, if you think that if you have a broader prior, so you have more uncertainty about your prior, then you're going to rely more on your data. So it's sort of the tension here is how much do you trust your data and how much do you trust your prior, and that's determined by this ratio. Yeah.
Hi. So sometimes I've seen recommendations for this, for the lambda or whatever, and the range parameter being chosen as whatever creates the maximum likelihood for cross-validated data. That seems like a weird. Is that a heuristic you're familiar with, or that?
Yeah.
This seems like a weird heuristic because then I wonder if I can then do cross-validation for model comparison afterwards.
Yeah. So the question is, how do you? So when you sometimes read about ridge regression, they do something different, which is that instead of specifying this weighting here on your prior as the ratio of these two variances, they define that as just a free parameter which you set somehow, and that might be by cross-validation. And that's fine if your goal at the end of the day is to get good predictive accuracy, then this might be the way to go. Now, of course, you want to make sure that if you're fitting that parameter to cross-validation, it should be some kind of nested cross-validation, or you should have some other data set that you're not fitting it to, and that's where you're evaluating prediction accuracy. I'm kind of operating within this Bayesian framework, which says that you should these parameters have a generative interpretation, and so if you can manage to pin down your assumptions about these relative sources of noise, then that will dictate to you what the lambda parameter in ridge regression should be. But of course, that might not be so helpful in practice, because how do I know what my tau squared, my sigma squared are? I don't know. So there are Bayesian versions of this where you basically try to estimate these parameters from the data.
Hold an extra point.
Yeah. You have a question?
Yeah. So I was wondering thinking about from a Bayesian perspective, rather than doing this sort of penalization, why not just put regularizing prior on the beta coefficients themselves?
But this is a the question is why not put a regularizer on the beta coefficients? But this is a regularizer on the beta coefficients, right? Or maybe I'm misunderstanding what you're saying.
I guess just like in a classical linear regression.
Yeah.
You just put a regularizing beta hierarchical prior.
Yeah, but how is that different from this? This objective function is minimizing the sum squared error plus a regularizer that's a penalty on the magnitude of the betas. And you can have different kinds of penalties too, right? Like if you make different distributional assumptions, like if I assume that the prior on beta is a Laplace prior instead of a Gaussian prior, then I get an absolute value of beta instead of the squared value. Yeah, I don't know if maybe I'm misunderstanding, but maybe we can talk about it later. So here's just an example using simulated data. So I generated some distribution of coefficients from the Gaussian, and this is the sorted coefficients here. This is the maximum likelihood estimate in green, and this is the map estimate in blue. So you can see that the map estimate gets closer to the true distribution of coefficients than the map estimate. And the critical thing here is that basically the maximum likelihood estimate is too sensitive to noise in the data. It's basically fitting really strong positive or negative coefficients, and that's basically systematically biasing it. here's another thing to illustrate the credible interval. So what I'm showing you here are the sort of regressions, but now I've put this 95% credible interval. So this is saying that I have some uncertainty about this parameter value, and what I can say is that I'm 95% sure in some informal sense, like that basically the posterior probability within this region, that the posterior probability that the true coefficients lie in this region is 95%. Okay. So what are the practical recommendations here? So if you have prior knowledge, you should use it. You shouldn't be shy about prior knowledge. As long as you can justify it, you should use it. But you should also, you should also try to use quantitative assessments to make sure that your prior knowledge isn't putting you off in some systematic way. So cross-validation is a useful check on all these Bayesian methods. Bayesian methods place a lot of emphasis on being really explicit about your generative assumptions. And within the Bayesian framework, you can do model comparison to test those generative assumptions. But it's often useful to kind of step outside of the Bayesian framework and do cross-validation and make sure it is a kind of sanity check that your assumptions actually are leading to better predictive accuracy. Because if they're not, then they're not that useful. So full Bayes is computationally hard. That's why we do various kinds of approximate techniques. And I told you about point estimation. There's a whole universe of approximate inference techniques like variational methods, Monte Carlo methods that I wasn't going to talk about today, but I'm happy to answer questions that you have about them. And then I think the practical recommendation for model comparison is that wherever possible, you should report BIC in cross-validation, and maybe even use the Laplace approximation. Laplace approximation will typically agree with BIC. And if you're computing BIC and Laplace approximation, then I suggest doing the random effects Bayesian models comparison that I mentioned before, because I think that's a really useful way, an increasingly standard way to report model comparison results. Okay. There's a whole other, how am I doing on time? I should go to 45 minutes, is that the time? Are there any questions?
Maybe in another 10 minutes, but
yeah, I mean, I was basically gonna just say this part is a lot shorter. I was just gonna talk a little bit about hierarchical models. Shall I do that and then we take questions? No, you can. Yeah, go for it.
When I use SPM BMS, I find like I still get really extreme exceedance probabilities.
Yes.
They get very close to 1.
Yes.
And like, we had Cody coming in saying he was feeling a little uncomfortable about those. Like, what do you think about those? Those tend to get really close to 1. Do you think that's valid? Do you think that's like?
Well, they're valid. It just happens to be the case that protected or exceedance probabilities are really nonlinear functions of the underlying marginal likelihoods. That's valid in the technical sense, right? They're computing what they say they're computing. Whether or not you want to use that as your metric of comparison or not is a different question, right? You may be more comfortable reporting something else, like the frequency of within the population.
It's weird when the ranks and one's just slightly better than the other, and it's really extreme. Like the difference in the posterior, like the map or whatever, between the two should be relevant, or just the ranks, or?
Well, it will be different because what you're giving it is the marginal, some approximation of the marginal likelihood. So it's not going to be sensitive just to the difference in the map estimates, but also to the, for example, the number of parameters.
But the BMS or the Bayes model spectrum can get the rank of the different models. Is that right?
Well, what it's taking as input is the marginal likelihood, the log marginal likelihoods, which rank them, but they're continuous value parameters that tell you about the distance between the models. Yeah.
So you mentioned that the BIC is pretty sensitive to dependencies of the data, and of course,
it ignores the dependencies.
Or ignores the dependencies, right? So, but it means you'll get a probably better number. Or it's going to go in some way that's not what you want.
Yeah.
And cross-validation obviously also has issues with dependencies.
Yeah.
I guess in practice terms, do you have an intuition that one is easier to deal with in real-world data things?
Yeah, I mean, there's also what's easier is not always what's best. I mean, obviously the easiest thing is to ignore dependencies and just apply the BIC, but that's not necessarily the right thing to do.
So, for example, like in playing with cross-validation, we've done things like where we took some cross-validation folds from like financial forecasting.
Yeah.
So if you assume that there's some like autoregressive part that you assume that's stationary, then you can basically in the training test just ignore that data so that there's no dependency.
Yeah.
But that's not. I mean, but again, that's really specific to that type of problem.
But the problem is that if you do this, the thing is that for some kinds of time series models, you need to to make predictions about the stuff that happens later, you need to condition on the stuff that happened before. So it's really hard to do a clean split of the data. There's other techniques though. I mean, there's this technique. I'm forgetting exactly the name. Something like one step ahead prediction or something like that.
That's more of that's on the same family.
Yeah. So, but and that's totally compatible with time series models. So essentially, the idea is to do cross validation, but you're just kind of doing it in a linear fashion. So you fit to the first n data points and then test on the n+1 data point. You kind of iterate through that way. I think that's a perfectly reasonable way to do it. Yeah,
and that's actually also simple.
Yeah, yeah.
Doesn't the Laplace approximation do better comparisons between combinations?
Not necessarily for. well, yes, in a sense.
It does.
The Laplace approximation doesn't make any independence assumptions.
Yeah.
Because it's not counting data points. It's just computing log likelihoods and then taking this Taylor series expansion around the log likelihood.
And I thought because of the Hessian, it should do better if there are dependencies than Gershman.
You should, in theory, yes, you should be able to. There's some issues with applying the Laplace approximation in practice, which is that typically you have to actually like it's too much of a pain for most models to actually compute the Hessian analytically. So what you can do is some kind of finite difference thing to estimate it, and MATLAB can do this for you, but it can sometimes be unreliable. So that's one caveat. And sometimes you can get degeneracies where you can't compute the inverse of the Hessian, and then this whole thing blows up, basically. So I've been grappling with that recently. Yeah.
I was wondering, when we're using Bayesian approach to do the parameter estimation, how we're going to set up the priorities. Say we say something from the Gaussian distribution, and how we're going to select the mean and variance.
Yeah. So the question is, if we're going to be Bayesian, where do we get the priors? And actually, that's a good segue to the last thing I want to talk about, which is that what we really like to do is estimate the priors, just like we've estimated the parameters. From the Bayesian's perspective, anything that you don't know, anything that you can't observe but want to infer, you have to do Bayesian inference over. So we can just take that notion straightforwardly and apply it to unknown to priors that have unknown parameters, and that's where hierarchical models come in. So let me just try to motivate this in a slightly different way in terms of estimation of parameters for different subjects. So we often estimate separate parameters for different subjects, but that's actually wasteful because we typically aggregate after that, and under the assumption that the subjects are similar in some sense. Now, the other extreme, something that's not typically done is to fit all the subjects, aggregate all the subjects into a super subject and fit a single set of parameters there. But there is an advantage there because now you've got lots more data to estimate the parameters. And depending on your experimental design, you might have only a small number of data points. So, if the data are noisy, the single subject parameters could be really unreliable. So we have this tension between the unreliability of single subject estimates and the inflexibility of the group level estimates. This is something that's called no pooling when you fit everyone separately, and complete pooling when you fit everyone together. The hierarchical models occupy this middle ground, which kind of combines the strengths of both of these approaches. So the idea here is we have some population parameters, and the subject level parameters are draws from this distribution. So what we're going to do is estimate the subject level parameters and the population parameters simultaneously. I came across this, someone on the internet made this really nice visualization of X-Source models, and I wish I could remember that person's name. Maybe some of you have seen this before. So what they did is here are a bunch of different subjects, and this is what they're plotting here is the relationship between days of sleep deprivation and the average reaction time for each subject separately, and they're comparing a no pooling model in red, so that's where you basically fit one regression line for each one of these subjects, versus a complete pooling model in green, that's where the same regression line is used for all the subjects, and then a partial pooling, which is basically fitting one of those hierarchical models. We're now in the partial pooling model, you have something that's in between the two extremes, right? So it's not going to look different for every subject, but it's going to look similar to the complete pooling model. model, it's going to basically pull this nose pulling model line, the red line, towards the green line. I just want to zoom in here on a few different examples to illustrate why this is really useful. So here's an example where the subject's data is basically going in the opposite direction of the global trend. So most of those lines were monotonically increasing. This one is decreasing a little bit, but it's kind of flat, basically. So the complete pulling model would totally miss this, right? It's just a terrible characterization of the subject's data. Now, the no pulling model will calculate that quite well, right? But the problem is that this is actually really unrepresentative of the population, so making some kind of population level inference based on this data is not a really good idea. And what the partial pooling model does is kind of flattens this out. So it says that basically it's not quite, you shouldn't draw as extreme an inference about the slope of this line for this subject because it's a pretty unrepresentative subject. And then sometimes the partial pooling and no pooling can line up quite nicely together. Here's an example. On the bottom here are nice examples where basically if you did no pooling, then there's really no way to make any good inferences about this data. Because in this case, there's a single data point. So you know, the no pooling line is kind of irrelevant. You can't infer slope from a single data point. So what you'd really like to do is say that basically if I don't know much about the subject, they should look more like the population. And that's what the partial pooling model is doing. It's saying that like in these cases where I have very little data, I'm going to regularize my estimates for that individual subject towards the population. And here's another visualization of this. So this is showing you the no pooling estimates, parameter estimates. This is slope and intercept, this two-dimensional space. The no pooling estimates are getting pulled towards this epicenter, which is the complete pooling model. And these are the partial pooling estimates. So it's kind of, you can think of it as kind of like this gravitational field that's pulling all the parameter estimates towards the complete pooling estimate. And I think, so how do you actually choose the population level distribution? I see this as basically a form of model comparison. So if you can commit to a particular hypothesis about that population level distribution and then try to do model comparison to compare different kinds of assumptions about that. But practically speaking, it's often sufficient to define some univariate Gaussian distributions on these parameters, and that's what certain packages will implement. If you use some kind of probabilistic programming language like Stan or Bugs, and I've implemented something like this in my toolbox, then you can be fairly flexible about how you define those population level distributions. And I think I just will not go into the details of the actual fitting. I think I would actually, my practical recommendation is figure out how to use something like Stan if you can, because that will do all the computation under the hood. And the beautiful thing about probabilistic programming languages, whether you use Stan or something else, is that it forces you to think generatively because that's the only way that you can express models in that language. So you never write down an estimator, you never write down an estimation algorithm, you never write down an objective function, you only write down generative models. Okay, with that I'll stop here. Yeah, did I?
Question I have is, say you fit a model with partial pooling, for example, and you want to make a prediction on a new subject. Typically, you're using something like, let's say, like LDR, R, something like that. You're using level coefficients to make predictions of the person. What impact, if anything, does partial pooling versus like a standard regression that just does complete pooling have on now prediction for a novel person? These fits are like individual fits of the data you have that doesn't even fit the model already. You want to use the data number to make novel predictions.
Yeah.
You know, like even like whole range machines, like their prediction are typically doing something sort of like complete pooling where you have like an SVM and you use all of your subjects' data together.
Right, but you don't have to, right? I mean, the problem is that you're going to be, you may draw incorrect inferences if you pool everyone together because you're ignoring the variability across subjects, right? So that's the key idea. If you think there's variability across subjects, it could give you biased estimates of those parameters. That might not matter that much for the prediction task, but I think it's an empirical question. Emma?
So you've talked a bit about hierarchy from the point of view of the subjects.
Yeah.
But recently, like Tyler Fleming and Nick Westphal had that paper that came out recently about how ignoring the sort of hierarchical structure of items can be quite bad.
Yeah.
But it seems like from that point of view, when you have to consider the whole time scale, get really intractable computationally.
Yeah.
I hope for that to not be the case at some point in the future.
Yeah, I hope that. Yeah, it's interesting. Yeah, I mean, I'm sure any of you who have used like mixed effects modeling in R know that convergence failures is a common failure mode, and that's purely an algorithmic question, I think, or rather, I'd say it's a combination of algorithmic problems with R. I've been told that MATLAB has a better routine, but I can't vouch for that. And then also like putting in proper regularization. So depending on how you define the model. How you put priors on the parameters and the covariance structures and stuff like that. The problem that the thing that I don't really like about doing mixed effects modeling, like in R, for example, is just that it's kind of opaque what exactly the generative model is that you're writing down, and probably most people couldn't explain it to you if you asked them. So that's why I prefer using these policy programming languages where it's just really explicit about what those are, and then you can more easily explore different kinds of assumptions. There's pros and cons there, right? So on the one hand, the pros, you can then, if you're just getting started, you don't understand all the stuff, you get going on R, which is great. Yeah. But on the other hand, if you deal with convergence, you don't know how to solve it because you don't know exactly what's going on, how to change the priors. Yeah. And then if you know all that stuff, you can do it yourself, but then you're at the point where you can't optimize it because you're not that great at everything. You should be faster. There's 3 days to run. Yeah. Yeah, no, I think, well, my philosophy is that you shouldn't ever have to deal with optimization issues yourself because that's just not your job. That's not a good use of your time or intellectual capabilities. So there's some computer science, in the same way that like, it's not, I don't see it as my job to worry about fMRI physics. There's like a physicist who deals with the MR physics, and I want to just get the data in some reasonably good, I want all that stuff to go on under the hood so I can focus on what I do better. So I think that computer scientists should be dealing with optimization algorithms, and what you should be worrying about is their scientific hypotheses. What is the generative model? What are the generative assumptions? I don't think you should be choosing priors so that you get convergence. I just think that's a really bad precedent because it's sort of, it's backwards. You want to write down algorithm. Basically, the way that the field is going is that we're getting better and better probabilistic programming languages. What's getting better is not so much the language itself, but what's going on under the hood where the inference algorithms are getting better. And I dream of the day where basically the algorithms are sufficiently good that you can write down any model you want and it will figure out how to do that inference efficiently and reliably. But we're not quite there yet. I really love that. The reason I haven't totally gone over to these probabilistic programming languages is when I talk to some people who develop them and I say, like, the models where I really want to use them are the ones where I'm too lazy to derive the inference myself. And those are exactly the models that apparently break those languages because they're too complicated. So, yeah.
I'm wondering how you set up the hierarchical model. You want to estimate like certain parameters for drug stuff. Say one group is like under placebo, another group is under L-DOPA. And if you're using the hierarchical model, then you basically want the within groups by individual parameters towards the mean within the group or like across the group.
Yeah, you can have multiple levels of hierarchy. So one option would be to model each group separately, so you have a hierarchical model in each group. And you can also build a kind of 2-level, or I guess 3 levels depending on how you count, where everybody gets regularized to the common group level distribution. And there's people, one legitimate concern is that if you're interested in individual differences or group differences, then regularizing people towards a common mean could be really dangerous, right? Because you could be getting rid of those individual differences if you modeled the variability wrong. And that is a legitimate concern. But one thing you should also appreciate is that you can sometimes get better estimates of individual differences when you do this, because it's all about reducing the noise and increasing the signal. So if there's noise in the data, then regularization can help, the right kind of regularization. If your priors are correct, then it can help get rid of that noise and in fact basically denoise your individual estimates.
And how do you make sure what you're doing is correct?
Oh, of course, yeah. That's always the question. That the only way to really step outside the generative modeling framework is to do something like cross-validation. Otherwise, you have to use the tools where
the thing that you always have to accept within a general modeling framework is that you always have to make assumptions, and I think that's a strength of the framework, that you are really clear about what your assumptions are, and it gives you a framework for testing those different assumptions, but you can't escape from making assumptions. Yeah.
This is like a kind of question, and it's okay if you don't answer it. This is all like mostly from a basic framework. But so the hierarchical modeling can actually show that you can get more reliable estimates by including uncertainty. But then if you want to do a hypothesis test over, let's say over a model comparison or things like that, you obviously only have one number, so you can't do that over subjects, which you normally do.
Right, right.
Do you have any, like I can imagine like a jackknife procedure where you do the hierarchical iteratively over each subject.
Yeah, you could, so you can kind of combine these different Bayesian and frequentist techniques in different ways, like you're saying that I get, my Bayesian model comparison gives me a single number out of this hierarchical model that tells me how good that model is relative to other models. But if I wanted some kind of confidence interval around that, I could do some kind of bootstrapping technique to get confidence interval. I can basically treat that as an estimate, as a kind of frequentist estimator, and get confidence intervals around it using standard procedures. That might be super computationally intensive, but yeah.
And then do you have like an intuition or at least advice about? I think what you guys were just talking about is really interesting.
Yeah.
You know, so if you assume that it's Gaussian over the population, then by the hierarchical thing you'll get better estimates, especially with noisy data.
Yeah.
But if you assume that there's a mixture of different populations within the population, then obviously that's going to bias you towards some individual.
Yeah.
Do you have a way that you might check if that might be true or not?
Yeah, I mean, well, you can always just look at the data or look at the parameters. There's a nice paper, kind of underappreciated paper by Dan Navarro. It's the Journal of Mathematics and Psychology paper called Modeling Individual Differences with Dirichlet Processes. And the basic idea, unfortunately, this is not, I don't think, implemented in any generic package, which is why people don't use it very often. But the idea is that, kind of like when I was talking about modeling an unknown number of latent sources, you could have an unknown number of these clusters of individuals within your within your subject pool. So what it does is it basically tries to discover those automatically. It tries to automatically infer the number of different clusters, and so now you have regularization within those clusters, and so you don't get this kind of smushing together of different types of individuals. That's really cool. Yeah. Yeah, if I was really enterprising, I would implement a version of that.
I know, you would get some of these. Any other questions? So let's thank Sam, and then let's take about a 15-minute break or so while all